In this video today, we're going to be looking at these things. So what exactly is this thing? So this thing here is what we call a diffraction grating. So what is a diffraction grating? A diffraction grating is a series of slits which are very close to each other. So instead of just having our single slit or our double slit, diffraction gratings have lots of slits, all evenly spaced and close together. So, for example, these diffraction gratings I've got here, it's got three different sizes of them. One's got 100 lines per millimetre, the next one's got 300 lines per millimetre, and the other one's got 600 lines per millimetre. So that's how many slits we have per millimetre. So that's a lot. And this is only a small standard size one. So you can get diffraction gratings which are greater than this as well. So a diffraction grating is a series of slits which are evenly spaced and there's many of them. So, what about diffraction gratings? So when we pass light through a diffraction grating, you see that we have dots. So these dots are different from our fringes that we saw in double slits. How is this so? You notice that for my 100 lines per millimetre, I've got these reasonably close together now. So we have a series of dots which have no light in between, or very, very little light. So a diffraction grating, instead of having the lights tapering off to nothing and then coming back up again, tapering up, so the intensity decreasing slowly and increasing slowly, diffraction gratings have light, no light, light, no light. So this is because they have so many waves interfering with each other. The only times that we can have our points of light, as you can see here, is when our wavelengths are exactly the m lambda. So the path differences between our waves are exactly one wavelength, two wavelengths, three wavelengths, and so on. So diffraction gratings are different from our double slits because of this. Double slits have a slight increase and decrease with our intensity of light, and diffraction gratings only have the light. So if you graph this, you see that we have peaks, basically, spikes of intensity. So we'll start off with our central one that has a spike of intensity. We have nothing, move along, we have another spike of intensity, move along, we have another spike of intensity. So the diffraction gratings work this way. So if I have a diagram of the waves leaving our diffraction grating, so this is going to be quite simplistic compared to a normal diffraction grating, because remember, the one I was holding up before had up to 600 lines per millimetre. This is only going to have a few lines, just to save a lot of time, otherwise it gets very messy. So you can see the wave fronts. We have our monochromatic light source, which is coherent going into our diffraction grating. Our diffraction grating then causes diffraction at each of the different slits that we have. And you can see that the wavefronts now are curved, so that each of the crests were going to be indicated by the lines. And as they interfere with each other, we get either deconstructive interference or constructive interference. So constructive interference is where our waves meet each other, and at that point we get an increase in the intensity of the light, and we get the deconstructive elsewhere where our crests and our troughs are meeting up and we get annulment of waves. So diffraction gratings work similar to Young's double slit, but there's a lot more of them. So we'll need to know the formula. So d sine theta is equal to m lambda. So this is the same as the other formula that you derived, and you derive this in the exact same way as that, but our d is going to be 1 divided by the number of slits. So in my case of my 600 lines per millimetre, you're going to have 1 divided by 600 to get the space of one slit. So the distances between one and the other slit. So that's one thing you need to remember about this. The differences between the double slit and the diffraction grating is your D is going to be 1 over N, N being the number of slits in your diffraction grating. So remember, the formula D sine theta is equal to M lambda has plenty of LiveScribe videos to go with it. So, now moving on. If we shine white light through a diffraction grating, we get some interesting aspects happening. So white light, so light that we see that has, if I get this in, so here's my studio lights I got here. They're white, aren't they? Alright, so white light is actually made up of all of the different frequencies of our observed visible light spectrum, from about 400 nanometers up to about 700 nanometers. So 700 nanometers is our red light, 400 nanometers being our violet light. So, if white light is made up of all these different spectra with different wavelengths, so all these different lights, wavelengths, and we shine this through our diffraction grating, our first point of maximum that we see, right in the center, is going to be just white light. It's not going to change. If we then move on to our first order maxima, we see something interesting. We get the colours of the spectrum separating into their different wavelengths. Starting with violet. Violet having the smallest wavelength is going to come out first. So you get our violet, our blue, our green, our yellow, our orange to our red. So red's going to be the furthest away from the central band. So that's going, or the central maxima. So the red is the longest wavelength of around 700 nanometers. So we get this. If we then look at the second order of this, which is going to be a bit hard from my little crude experiment I've got here, but the second order does the same thing. Violet first, followed by the others, lastly red. So this is what happens when you shine white light through a diffraction grating. So the smallest wavelength goes out first to the smallest angle, the longest wavelength goes to the largest angle. Now this is useful in spectroscopy, which is going to be our next topic right now. So in spectroscopy, we use a spectroscope to find out the spectra of an emitting source. So this is used in chemistry if we look at a atomic absorption spectroscopy. So we've got a source of an unknown sample, we're putting it into a flame, and we're looking at the emitted spectra from this then. We can then analyse the spectra that we get out to find out what was actually in our sample, because each of the different elements has a certain absorption spectra, an emission spectrum. So we can then match up what we had in our experiment to the known values of each of the different emission spectras of the different elements until we get a match of all our different lines of the wavelengths of the light that was emitted from our spectroscopy experiment. So the diffraction grating actually helps us do this, because if we just show light at it, we're not going to get the separation of the wavelengths of the light. We want the separation so we can identify each individual wavelength. So, like I told you before, when you shine white light at a diffraction grating, you get the separation of the white light into the spectrum. But, oh yeah, and when we do it in spectroscopy, we're only going to get the emission of the wavelengths that we want to see, not just the whole spectrum. So why do we use a diffraction grating in spectroscopy? There's some few things. More of it on page 59 of your textbook, book 2, but I'll just go through a couple. So you saw before that a diffraction grating has defined lines. This makes it easier for us to determine the exact wavelengths of the emission that we want to actually see. So, and there's also a formula that matches up these lines to what we want to know. so we can find out the exact wavelength of the emitted lines. So diffraction gratings are useful for that. If we just use a prism, so we can use a triangular prism with a light source to separate the light out, which is what Newton did, and I can actually show you that in the lab if you really wanted to. Just say, hey, I want to see that prism experiment, eh? So, if we use the prism, there's actually no formula that links up the emitted wavelengths to the actual size of the wavelength that we want to find out. Diffraction gratings, there is. D sine theta is equal to m lambda. So this is why diffraction gratings are useful in spectroscopy, because we can actually link up the information to what we see, and we can find out useful stuff. Never know when you might need to know this. So one other thing we're going to look into is speckle. It's a little bit off the topic slightly, but I don't really have any other videos I can shove this into. It's only a short thing. So, speckle. If we shine a laser at a rough surface, we get what we call speckle. So the laser beam is going to be the coherent light beam heading towards our rough surface, and then it's reflected off of this rough surface. Because the surface is rough, we're going to have some of the wavelengths of our parallel beams being messed up a little bit, and we're going to have interference on the reflection. So this is speckle. So the key points from the video today. These things, diffraction gratings, are useful. So, what is a diffraction grating? Diffraction gratings are many thin slits. They're evenly spaced, and they're more impressive than what a double slit is, because we can do some more interesting things. So, the observed pattern that we get out of a diffraction grating is we get defined points where we have no light in between them. We only get points of light where we get the constructive interference. Everywhere else we have deconstructive interference because we have so many light waves leaving each of the different lines. So we get one here, one there, one there, one there, and they interfere with each other because of diffraction. So we're only going to get the point of light where we have our path differences equal to m lambda. Right. The formula d sine theta is equal to m lambda is important. You need to know how to derive this formula. You also need to know how to use this formula. So the differences between the formula here and when we're doing it with double slits is that our d is going to be equal to 1 on the number of slits. So you need to be able to draw the graph of a diffraction grating. So the pattern that we get from a diffraction grating, we need to change it into a graph, which is going to be spikes of peaks of intensity from the light. White light, when we shine it through a diffraction grating, separates into the colours of the spectrum. And we can get our violet light coming out first because it's got the smallest wavelength, and our red light has got the higher angle because it's got a longer wavelength. This is useful in spectroscopy. So spectroscopy is where we analyse a sample to find out the wavelengths of the light that are in it, and we use a spectrometer for this. Spectrometer has a diffraction grating in it. So if we look at a sample of light through a spectrometer, we're going to get defined lines of the wavelengths of the light that's being emitted. So using a diffraction grating in spectroscopy is useful because it's more analytical than what, say, using a prism is, because we actually got a formula that links our wavelength to what we're seeing. So, and then lastly, speckle. Speckle is when we have laser beams being reflected off of a rough surface. This is due to the interference of light that we get this speckle pattern. So, our next video is going to be on how DVDs and CDs work, and possibly Blu-ray if I'm that excited about it.